This video will begin our discussion of planes in R3, which is 3 space. So the first thing that we're going to talk about is the equation of a plane. We're going to derive it. To get there, though, we need to know what a normal is. A normal is another word. It's for a vector that is orthogonal to a plane. So a vector is orthogonal to another vector, but a vector is normal to a plane. Two different definitions you can interchange. We typically just call them normals. Okay, so a normal is a vector that is orthogonal. Remember, it means the whole plane, which is just like an infinite sheet of paper, that vector would meet it at a right angle. I could put it anywhere. Remember, vectors don't live anywhere in space. I can put it anywhere on that plane and it would meet it at a right angle. All right, so we're going to start here. Given 1 point on a plane, so we have, this is going to be our specific point, and then a normal vector to the plane. So this vector is normal to every vector that's on that plane. So we can define a specific plane from that. Okay. So first thing we're going to do, we have a specific point. I need a general point. So here's my general point. Let this point be any point on the plane in question. On the plane. Then we can create a vector that's in that plane by creating the vector p naught p from that. Okay, so p naught p would be x naught minus x, y naught minus y. Let's flip those. I think I have them backwards. Yep, I do them backwards. All right, so remember p first. So x minus x naught, y minus y naught, and z minus z naught. There we go. Okay, that is my vector then. Since that is a vector in the plane, right? I use 2 points in the plane to come up with this vector. Since it is in the plane, we know that the vector that we created is orthogonal to my normal vector that we defined above. Just by definition, that means that p naught p vector dotted with normal vector, since they are orthogonal, we know the dot product is 0. I can now replace that. Let me put that down here. It's going to make more sense logically. That tells me that. And then I can fill these in. X minus x naught, y minus y naught, z minus z naught. Move this over. Dotted with a, b, c, that's going to equal 0. Just by definition, right? We created a vector in the plane. We know that vector is orthogonal to the normal vector, which means the dot product is 0, and then I just wrote the definitions in. And this dot product, remember, is just take your components and multiply them. A times x minus x naught, plus, because it's a dot product, times y times b times y minus y naught, plus c times z minus z naught equals 0. This is my equation. Equation of a plane. So that is 1. So we'll highlight that. And then we actually have 2 forms of this, just like the equation of the line. So there's 1. And then we can multiply this out. If I multiply it all out, we can get down to a form. I'm just going to do dot, 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 because we're going to multiply it once, and then I'm going to do dot, dot, dot. I can get down to ax plus by plus cz. And then there's going to be some number adding this ax naught, by naught, and cz naught, and we're just going to call that d and move it to the other side. Here are 2 forms. Okay, so one is standard form, and one is general form. So let's write this down. Standard form, let me get rid of these arches. Standard form, general form. All right, so that's how we come up with our equation of a plane. Notice this one is an equation. What gets mixed up quite a bit here is people think this is a line since all the powers are 1. But that actually doesn't make sense. Think about if I say x equals 5, and I mean in 1 dimension, I would literally graph a number line and put a 5. but x equals 5 in 2 space is a line. Here, let me draw this instead of just saying x equals 5 in 1 space is literally a point. That's 1 space. 2D, x equals 5 becomes this like line in 2D, no longer a point, right? There's my x and y axis. We're used to graphing x equals 5. So it would make sense that if I were to extend it another degree and do that was 1D, 2D, 3D would be a plane. No longer a line because it was a line in 2D. So it makes sense that things to the first power, x to the first power, y to the first power, z to the first power, altogether will produce a line in 3 space. A plane in 3 space, a line in 2 space, a plane in 3 space, a line in 2 space, a dot in 1 space. One variable, x to the first. Okay, so those are our forms. Let's lead into an example. So I have typed up there for you, nice and pretty. General form, standard form, given everything. We're going to work a few examples here. Find the equation of a plane with a point, and that's parallel to that. So for plane, this may be a good note to take. Need a point, and not a directional vector this time, but a normal vector. So we need a vector that is orthogonal to the plane. Okay, so they want it parallel to, notice this is not a line, this is a plane. We can create a normal vector out of that. My normal vector, remember, are my coefficients, 2, 3, -2. That was the a, b, and c from my formula right above, right? If it's in this form, the normal vector is a, b, and c, the numbers in front of my coefficients. This one's in this form, so we still pull a, b, and c. All right, so we have that, and we want to create an equation of the plane. I have both of those, so I just fill it in. So 2 times, okay, it's going to be x minus 1, that comes from here, plus 3 times y plus 2/3, that came from the middle point component, and then minus 2 times z plus 1 equals 0. We could also work this down to, that was standard form. Let's work it down to general form by just multiplying it out. 2/3 works out nice and pretty for us, thankfully. We add our x, y's, and z's stay on one side, 2x plus 3y minus 2z. If I add all my coefficients up, these go away, I get minus 2. If I bring it over, I get 2. This is general form. General form. All right, so there are 2 forms. They're both useful. The bottom form is nice and pretty. You can pick up information really quick. Standard form is really nice because not only do you get the normal vector, you can also get a point on the plane, which we don't get down in the general form. All right, here's one of a common application for this. Find the equation of the plane containing, okay, they gave me 3 points. So I'm going to write what I need. So I need a point for the plane, and I need a normal vector. Now, this one didn't give me a parallel to this plane. It didn't even describe a vector at all. It just gave me 3 points. But I can create vectors in the plane. So we'll use point P. We'll have that. We'll use that. I'll write that. 3, -1, 2. We'll use that point. And then we're going to create some vectors. PQ is a vector in the plane. All right, so let's do that. 2 minus 3 is -1. 1 minus -1 is 2. 5 minus 2 is 3. That is just subtracting Q minus P. That is a vector in the plane. PR is also a vector in our plane. 1 minus 3 is -2. -2 minus -1 is -1. And -2 minus 2 is -4. These are vectors in the plane. All right. To find a normal, I'm going to use the word orthogonal because I hope it's something in your brain's going off on how to do this. Orthogonal, to find an orthogonal vector or normal vector, how do I find a vector that is orthogonal to 2 vectors? Well, find the cross product. PQ crossed with PR. That will give me a normal vector. All right, so let's do that. I'm going to shrink that line up because I'm going to need the space. All right, so we're going to cross those two. PQ crossed with PR. My determinant I, J, K. And then we got -1, 2, 3. And I got -2, -1, -4. All right, so I run through this process. -2, -1, 3, -4. That's covering up I column. Then I do a minus, cover up J column. And then cover up the K column. I got -1, -2, 2, -1, K. All right, we just go through this process now. Our little determinants, I got -8 plus 3, I, minus 4 plus 6J, plus 1 plus 4K. So that vector is -5, -10, 5. This is my normal vector, and I have a point. So I'm going to use this point and this vector. It doesn't tell me what form to use, so I'm just going to put it in standard form and stop. So I got -5 times x minus 3 minus 10 times y plus 1 plus 5 times z minus 2 equals 0. So this is the equation of the plane, given those 3 points. The key to this is knowing that I can create two vectors given the points, and then I can use the cross product to find a normal vector, because a cross product always spits out an orthogonal vector to the two vectors involved.